Hello everyone, I am Prakhyath Jain, Assistant Professor, Department of Mechanical Engineering, AJIET Mangalore. Today I am going to discuss about Module 1, this Class 1, this is the introduction portion. So in this video, I am going to explain about compressibility, bulk modulus and derivation of bulk modulus for two important processes, that is isothermal process and adiabatic process. Then manometer, mechanical gauges. In mechanical gauges, I am going to explain about Bourdon gauge and related problems. First, let's go for compressibility and bulk modulus. So before defining compressibility, now let us just discuss about bulk modulus. So what is bulk modulus? Bulk modulus is defined as ratio of compressive stress or compressive pressure to volumetric strain. So what is volumetric strain now? Volumetric strain equal to change in volume divided by original volume, or it is a ratio of change in volume to original volume. So now bulk modulus, that is represented by capital letter K, that is equal to compressive stress or compressive pressure divided by volumetric strain. Now compressibility. So compressibility is the reciprocal of bulk modulus, that is compressibility equal to 1 by K. Now consider a cylinder fitted with a piston as shown in figure below. There is a piston cylinder arrangement which consists of gas inside. Let V equal to volume of gas enclosed in the cylinder. There is a specific volume, small letter v, or you can use letter like this. Small letter v equal to volume of gas enclosed in the cylinder. Small letter p equal to pressure of gas when volume is v. So when volume of the gas inside the cylinder is v, pressure exerted by that gas is small letter p. Let the pressure is increased to p plus dp. The volume of gas decreases from v to v minus dA. So when the pressure is increased, that is by moving the piston inside, you can increase the pressure. So when the pressure increases, volume decreases. You can see the volume decreases by amount dV. So there is a small letter dV. So when pressure, you are going to increase the pressure by pushing or moving piston inside, so that volume decreases. Pressure and volume, that is inversely proportional. So let the pressure is increased to P plus dP. The volume of gas decreases from V to V minus dA. Initial pressure was P. So because of movement of the piston inside, pressure increases. There is an increase P plus dP. And because of increase in pressure, volume decreases. That is, initial volume was V. So decrease in volume is dV. So volume is V minus dV. Then the increase in pressure, so that is equal to dP. So you can take final pressure minus initial pressure. Final pressure is P plus dP minus initial pressure, that is P. So increase in pressure is dP, that is unit is Newton per meter square. Next, decrease in volume. Final volume, that is V minus dV minus V, that is the initial volume. So what is a change in volume? That is dV. There's a negative actually because it is decrease in volume. So dV. Therefore volumetric strain equal to minus dV divided by V. So that is a change in volume to original volume. Negative sign means the volume decreases with increase in pressure. That's what I told in explanation. When the pressure increases, volume decreases. Pressure is inversely proportional to volume. Here we are increasing pressure, so volume automatically decreases. So we are going to use negative sign in that expression. Therefore, bulk modulus is equal to increase in pressure to volumetric strain. So increase in pressure is dP, volumetric strain is minus dV divided by V. So that is equal to minus dP. So minus dV divided by V goes to numerator. So minus dP into V divided by dV. So unit of bulk modulus, this is very important. Unit of bulk modulus. So bulk modulus equal to increase in pressure to volumetric strain. Strain means it has no unit. So unit of bulk modulus is same as that of pressure. So that is increase in pressure means unit of pressure is Newton per meter square. If it is in Newton per centimeter square, then bulk modulus unit also becomes Newton per centimeter square. But SI unit of bulk modulus is Newton per meter square. So you have to remember this. I have already told about this thing in dimensional analysis. Bulk modulus equal to Newton per meter square. There is a SI unit. So compressibility equal to 1 by K. So compressibility is reciprocal of bulk modulus. Therefore, unit of compressibility equal to, that is 1 divided by Unit of bulk modulus. Unit of bulk modulus is Newton per meter square. So unit of compressibility becomes meter square per Newton. So there's a unit, very important, unit of bulk modulus and unit of compressibility. Next, relationship between bulk modulus, that is represented by capital letter K, and pressure, that is small letter P, for a gas. There are two important processes. About this I already explained in 5th module, that is a compressible flow. So let me just go through this concept again. First one, for isothermal process where temperature remains constant, that is T equal to constant, or it is called as hyperbolic process, or is PV equal to constant process, or temperature equal to constant. So you can represent n number of ways: hyperbolic process, or T equal to constant, or PV equal to constant. So isothermal process, temperature remains constant. The relationship between pressure, that is small letter P, and density rho of a gas is given by equation P by rho equal to constant. So P by rho equal to constant, that is for isothermal process. Now what is rho? Rho equal to you can express rho in terms of volume. There's a specific volume. Unit of density is kg per meter cube. So unit of specific volume is meter cube per kg. So specific volume equal to 1 by rho. That is 1 by rho means unit of rho is kg per meter cube. So 1 by kg per meter cube means it is meter cube per kg. So in place of 1 by rho, I can substitute as small letter v. There's a specific volume. So PV equal to constant. That is for isothermal process. Initially start with P by rho equal to constant, but 1 by rho equal to small letter v. That's a specific volume. So now PV equal to constant. Differentiating this equation, we get, treating P and V both are variables. We have to treat here P and V are both as variable. So product rule, P into dV plus V into dP equal to 0. Just applying product rule. So first taking P term, then differentiating V, then taking V first, differentiating P. So P dV plus V dP equal to 0. Or just rearrange P dV equal to minus V dP, or P equal to minus V dP divided by dA. So P equal to minus V dP divided by dA. Substituting this value of P, that is equal to minus V dP divided by dV in equation for bulk modulus. So what we are going to get? So bulk modulus equal to K equal to increase in pressure divided by volumetric strain. So that is equal to, increase in pressure is dP, volumetric strain is minus dV divided by V. So that is equal to minus dP divided by dV. So V goes to numerator. So minus dP into V divided by dV. Now we got minus dP divided by dV into V as P. So you can see that P equal to minus V dP divided by dV. So K equal to P. So we get K equal to P. That is bulk modulus equal to pressure. That's the expression for isothermal process. So you can directly substitute K equal to P in case of isothermal process if they ask the value of bulk modulus for isothermal process. Second one, for adiabatic process. So what is adiabatic process? It is called as isentropic process. This is S equal to constant, entropy equal to constant, where there is no heat transfer from surrounding to system or system to surrounding. For example, I already explained about this thing in basic thermodynamics. There's a thermos flask. There is no heat entering from outside to inside or inside to outside. It is not going out. So same thing, adiabatic process, Q equal to 0. So the relationship between pressure and density of a gas is given by equation P by rho to the power gamma equal to constant. So P by rho to the power gamma equal to constant. But what is 1 by rho to the power gamma? That is equal to V to the power gamma. Same expression, rho equal to V equal to 1 by rho. So rho to the power gamma means it goes to 1 divided by rho to the power gamma. That becomes V to the power gamma. So P into V to the power gamma equal to constant. Differentiating above equation, treating P and V as variables, we get, first take P as first term. P into differentiation of V to the power gamma plus taking second term, that is V to the power gamma, into differentiation of first term, that is dP equal to 0, applying product rule, or P into, so again differentiating V to the power gamma. So what is the differentiation of V to the power gamma? So V to the power gamma means gamma into V to the power gamma minus 1. There's a differentiation of V to the power gamma. Similarly into dV. So differentiation of differentiation of V to the power gamma becomes gamma into V to the power gamma minus 1 into dV plus gamma to V to the power gamma into dP, that is as it is, that is equal to 0. Now just rearrange P into gamma V to the power gamma minus 1 dV plus V to the power gamma dP equal to 0. So now just divide by or cancelling V to the power gamma minus 1. So on both sides. So or you can just divide by V to the power gamma minus 1. So V to the power gamma minus 1 in first term there is a V to the power gamma minus 1. When you are going to divide by V to the power gamma minus 1, you are going to get cancel that term. So P into gamma due to the power dV, P into gamma dV plus V to the power gamma dP divided by V to the power gamma minus 1. So gamma V to the power gamma V to the power gamma you can cancel there. Remaining is V. So P into gamma dV plus VdP equal to 0. Just divide by V to the power gamma minus 1. That's it. So just rearrange P into gamma dV equal to minus VdP or P gamma equal to minus VdP divided by dV. What is minus VdP divided by dV? That is bulk modulus. So in place of bulk modulus relation, you just substitute P gamma. So substituting P gamma equal to minus VdP divided by dV in equation for bulk modulus. So bulk modulus K equal to increase in pressure divided by volumetric strain. So that is equal to dP divided by minus dV divided by V. So that is equal to minus dP divided by dV into V when V goes to numerator. So we get in place of minus dP divided by dV into V, we have to substitute P gamma. So K equal to P gamma, where gamma equal to 1.4. This is the ratio of specific heat. What is ratio of specific heat? That is equal to Cp by Cv. So specific heat at constant pressure to specific heat at constant volume. So gamma equal to 1.4 equal to ratio of specific heat. So for adiabatic process, bulk modulus equal to, that is just multiply pressure by gamma. This is ratio of specific heat. Whereas for isothermal process, bulk modulus equal to pressure. That is the initial pressure. K equal to P. So you have to remember these two processes, very important from examination point of view. And unit of bulk modulus is, it is same as pressure, that is Newton per meter square. Compressibility, it is reverse, that is meter square per Newton. So you have to remember that. Next, manometers. What are manometers? Manometers are defined as the devices used for measuring pressure at a point in a fluid by balancing column of fluid by the same or another column of fluid. They are classified as simple manometers, differential manometers. There are two important types of manometers, simple manometers and differential manometers. Now, first of all, what is manometer? So, manometer is a device used for measuring pressure at a point in a fluid by balancing column of fluid by the same or another column of fluid. So by balance of fluid column, that is right limb equal to, you might be remembering that topic, that is balancing pressure head on right limb equal to left limb. So you have to balance with respect to some datum. So that's the concept applied here, manometers. You have to just balance the column of fluid by the same or another column of fluid. By using that, you can get the pressure, unknown pressure or unknown head, that is H or P. So there's a concept here, simple manometers and differential manometers, two types. So this was a left out portion, so I'm repeating here. So advantages and limitations of manometer. This you can write in your own words. Still, I have listed here some of the points. Just let me go through that. So first one, manometers are simple, inexpensive and easy to attach. It is very easy to fit the manometer, and these manometers are simple and inexpensive when compared to other devices like pressure measurement devices. These have least cost. Second one, the results are not affected by vibrations. You can use these manometers in vibration environment. That is not going to change pressure values. Third one, they have good accuracy and sensitivity. So they are going to give the result with good accuracy and sensitivity, that they are going to sense the pressure very easily. They can be used to measure low as well as moderate pressures. So they can be used to measure the low as well as medium pressures. A fifth point, manometers require less maintenance. So compared to other pressure measurement devices, this requires less maintenance. So less maintenance cost. Limitations, manometers are fragile, bulky and easily breakable, because most of the manometers are made up of glass, so so they're easily breakable, and these setup are bulky, so it is of size is big when compared to other available pressure measurement devices, and it is easily breakable. Second one, readings of manometers are affected by change in temperature. So if you want to measure pressure in some temperature like room temperature, that is going to give pressure corresponding to that temperature, because pressure is directly proportional to temperature. If there is any change in temperature because of some heat from outside environment, so that is going to affect the pressure. So there's a disadvantage. As the quantity of manometric liquid changes, their sensitivity changes. So what is manometric fluid? Usually we are going to use the mercury as manometric fluid. Fluid inside that manometer is called as manometric fluid. So if we are going to vary that manometric fluid quantity, that is going to change the pressure value, that is sensitivity, the amount of time that is taken for sensing that pressure, that is going to vary directly with respect to manometric liquid. So those are the advantages and limitations of manometer. Now mechanical gauges. So next topic, mechanical gauges. Mechanical gauges are those devices which consist of an elastic element and deflects under action of applied pressure. So mechanical gauges, I'll explain about this thing in next slide with the diagram. So are the devices which consist of an elastic element. There's an elastic element and deflects under the action of applied pressure. So these are used to measure pressure. When there is a pressure variation, this elastic element that is going to deform. This moment is mechanically magnified and operates a pointer along a graduated circumferential scale. So that moment or deflection that is magnified, you are going to increase the quantity or magnitude by means of some arrangement, and operates the pointer along a graduated circumferential scale. So that deflection can be magnified, and that is shown by using a pointer. These gauges are used for measuring high pressure and in applications where high precision is not required. So these mechanical gauges can be used to measure high pressure, because manometers can be used to measure pressure that is low or medium quantity. So high pressure, there should be some device. So in that case, mechanical gauges can be used. The commonly used mechanical gauges are as follows. First one, diaphragm pressure gauge. Second one, Bourdon tube pressure gauge. Third one, deadweight pressure gauge. Fourth one, bellows pressure gauge. So those are the classification or types of mechanical gauges. The most commonly used type of mechanical gauge is a Bourdon tube pressure gauge. So I am going to explain about Bourdon tube pressure gauge in this video. This is the most commonly used pressure gauge. So Bourdon tube pressure gauge, it is a curved or twisted metallic tube having elliptical cross section. It is sealed at one end. So you can see there, twisted metallic tube having elliptical cross section. It is sealed at one end. So you can see that that's cross section of that curve shape. It is metallic and it is twisted and it has elliptical cross section, and it is sealed at one end. So you are going to seal at one end. The tube tends to straighten out on the application of pressure, and angular deflection of the free end is taken as a measure of pressure. So you can see that at one side there is a pressure measurement inlet. So when you are going to keep that device, there is a Bourdon tube pressure gauge, it is going to sense that pressure. Because of that pressure, the twisted metallic tube that deforms. So because of the deformation, at the other end there is a pointer. So pointer or a link, you can see the elliptical cross section is connected to one link is connected to pointer. Because of the deflection of the elliptical cross section, link is going to move. Because link is connected to pointer starts moving, so that you can measure the amount of pressure that is applied to Bourdon pressure tube. There's a principle of Bourdon tube pressure gauge. So The tube tends to straighten out on the application of pressure, and angular deflection of the free end is taken as measure of pressure. In the C-shaped tube, the angular deflection is measured with a mechanical pointer moving over a calibrated scale. So calibration is required anyhow here. Bourdon tubes are fabricated with metal alloys such as brass, stainless steel, phosphor, bronze, nickel alloys, etc. So those are the materials that can be used for fabrication of Bourdon tubes. The maximum amount of pressure measured by using this gauge is 3 meganewton per meter square, or it is 3 megapascal. Megapascal means 3 into 10 to the power 6 pascal, or 10 to the power 6 newton per meter square. So there's a maximum quantity of pressure that can be measured by using Bourdon tube. Bourdon tubes are more sensitive to shock and vibration than other types of gauges, and hence they are used for static measurements. What is static measurements? So there is no motion. So if there is motion means that tends to produce vibration. So this cannot be used in vibratory environment or shock environment, that is going to affect the deflection of the elliptical cross section or C section. Because of that, you are going to get wrong pressure value. So there is a drawback of Bourdon tube pressure gauge. So first problem, a vertical gap 2.2 centimeter wide of infinite extent contains a fluid of viscosity 2 Newton second per meter square and specific gravity 0.9. A metallic plate 1.2 meter by 1.2 meter into 0.2 centimeter is to be lifted up with a constant velocity of 0.15 meter per second through the gap. If the plate is in the middle of the gap, find the force required. The weight of the plate is 40 Newton. I already solved problems this kind of problem in module 1, but this is one extra problem because here thickness is given. In those problems I neglected thickness of the plate. So here thickness should be considered and weight of the plate is given. So dimension of that plate is 1.2 meter by 1.2 meter, that is area, and thickness it is given 0.2 centimeter or 0.2 divided by 100, that is meter. So vertical gap, we are going to keep that plate at the center, so our middle of that vertical gap, so that is 2.2 centimeter wide. So gap, that distance, horizontal distance is 2.2 centimeter. So total is 2.2 centimeter. Plate is in the center, so that is 0.2. So what is the left out gap? So 2.2 minus 0.2, so that is 2 divided by 2. So distance of that plate from center of that plate to from the top of that plate to the vertical distance or vertical plate or vertical stand, it is 1 centimeter. So either on the same way, like both the sides, it is 1 centimeter because 2.2 centimeter is the width of that vertical gap. So out of which 0.2 centimeter is thickness of plate. So 2.2 minus 0.2, that is 2 divided by 2 because there is the plate is at the center. So 1 centimeter from each stand on both ways. So width of gap equal to 2.2 centimeter, viscosity mu equal to 2 Newton second per meter square. Viscosity, that is dynamic viscosity, that is given in problem. So specific gravity of fluid, that is equal to 0.9. So therefore density of fluid, because specific gravity equal to density of given fluid to density of standard fluid. Standard fluid here it is water, density of standard fluid, that is water, is 1000. So density of fluid becomes, just cross multiply specific gravity into density of standard fluid. So 0.9 into 1000, that is equal to 900 kg per meter cube. Therefore specific weight or weight density of fluid. So specific weight or weight density, that is the formula for that is rho g. Already discussed about that thing in dimensional analysis as well as in pitot tube. That is equal to rho g. So rho value we just obtained, that is 900. G value is 9.81. Unit of specific weight is Newton per meter cube, or you can determine the unit by using the formula, that is rho g. Kg per meter cube into the meter per second square. That is the alternate unit of specific weight. 900 into 9.81 Newton per meter cube. There is a specific weight or weight density of the fluid. Just remember, I'll explain about use of this specific weight in calculation. Then volume of plate. So volume of plate area is given thickness is given directly. So 1.2 meter by 1.2 meter into 0.2 centimeter. Just see there is 0.2 centimeter, not meter. Remaining two values are in meter. So I have to convert 0.2 centimeter to meter. That is 0.2 divided by 100. So that is equal to 1.2 meter by 1.2 meter into 0.002 meter. So that is equal to 0.00288 meter cube. So area into length, that is the volume. So 0.00288 meter cube. Therefore thickness of the plate. So thickness of the plate, last one is thickness, that is 0.2 centimeter. So area into length or area into thickness, that is the formula for volume. So thickness is 0.2 centimeter, or that is equal to 0.002 meter. Velocity of plate, that is given as 0.15 meter per second. So there is a velocity. Then weight of plate, that is equal to 40 Newton. Now, when the plate is in the middle of the gap, the distance of the plate from vertical surface or vertical stand of the gap. So how to calculate? So that is total width minus thickness of the plate. So divided by 2, because on two sides, plate is in the center. So I have to calculate distance of that plate from the surface of the plate to the vertical surface. So vertical surface of gap. That is width of the gap minus thickness of the plate divided by 2. So that is equal to 2.2 minus 0.2 divided by 2. So that is equal to 1 centimeter, or that is equal to 0.01 meter. So you have to remember that formula, like width of the gap minus thickness of the plate divided by 2. Otherwise you can calculate that thing by using diagram. So it is a vertical plate, you have to remember, it is not horizontal. In previous problem I used horizontal plate. Here it is vertical plate, it is at the center. So now shear force on the left side of the metallic plate. So shear force on there are like two shear forces, one on left side and other one on right side. So in previous problem it was on upper side and lower side. Here left side and right side. So F1 equal to shear stress into area. So because shear stress equal to force by area, so that is tau equal to F by A. So similar way, so left side force I have taken at F1. So F1 equal to shear stress into area, just cross multiply. So since shear stress equal to F1 divided by area, so area equal to 1.2 into 1.2 meter square, that is given in problem. So F1 equal to mu into du by dy at 1, or it is left side, into area. So that is equal to mu, it is given as 2 Newton second per meter square, that is 2, into velocity du, there is a change in velocity u minus 0, that is 0.15, divided by change in the distance or gap, so 0.01. So that is from surface of the plate to left side vertical surface. So 0.15 divided by 0.01 into 1.2 into 1.2, that is the area. So that is equal to 43.2 Newton. Similarly, shear force on the right side of the metallic plate, let me take it as F2. So F2 equal to shear stress into area. So that is equal to mu into du by dy at 0.2, or you can write right side, into area. So that is equal to 2 into 0.15 divided by 0.01 into 1.2 into 1.2, that is equal to 43.2 Newton, the same value as that of right side. So F1 equal to F2. Therefore total shear force equal to F1 plus F2. So that is equal to 43.2 plus 43.2, right hand side force plus left hand side force, that is equal to 86.4 Newton. So there is a total shear force. The problem is still not complete, so we have to proceed further. So in this case, the weight of the plate, which is acting vertically downward, and upward thrust is also be taken into account, because weight of the plate is given. In previous problem and all, I neglected that weight and thickness. So I didn't consider that weight. But in this case, they specifically given weight of the plate. So if you're going to take weight of the plate, then you have to take weight is acting downward. So for every action, there is a equal and opposite reaction according to Newton's third law. So here for downward force, there is a counter force. That counter force is called as thrust force, or it can be called as buoyant force. I'm going to explain about this buoyant force in second module. So buoyancy, principle of buoyancy, or Archimedes principle. So I'm going to explain about that thing in second module. So upward thrust equal to weight of the fluid displaced. So in order to counter that upward thrust, there is a weight of the fluid displaced. Now what is weight of the fluid displaced? So when you are going to submerge any body into the water, so you can see the water coming out, because the water is just coming out, or you can just imagine throwing one stone into water, so you can see the spilling of water. So that is just because of the weight of the component or weight of the stone, whatever you are throwing into the water. Because of the weight of the stone, that is going to exert some force, so because of that there is a spilling of water outside. So same way, the upward thrust equal to weight of the fluid displaced. So that is equal to weight of the fluid displaced equal to weight density of the fluid into volume of fluid displaced. So weight density of the fluid into volume of fluid displaced. Now what is weight density of the fluid? That is Newton per meter cube into volume of the fluid displaced, that is meter cube. So meter cube, that is going to cancel. Now what is the remaining unit? That is Newton. So that is equal to weight of fluid displaced. So when you are going to keep that plate, how much amount of the fluid that gets displaced, you are going to calculate here. So that is weight of the fluid displaced equal to weight density of the fluid, you already calculated, that is rho g, into volume of the fluid displaced. So volume of the fluid displaced equal to volume of the plate. So it is the volume of the plate you already calculated. Whatever I explained, the stone concept you can apply here. Because of throwing of stone, you are going to get a reaction. So same way here also, volume of the plate equal to volume of fluid displaced. So that is equal to 0.00288 meter cube. The net force acting in the downward direction due to weight of the plate and upward thrust. So there's a net force. So you have to calculate that net force. So weight of the plate minus upward thrust. So what is weight of the plate minus upward thrust? So upward thrust equal to 900 into 9.81 into 0.00288. So that is equal to 24.43 Newton. So that is equal to, now you have to suppose to find the net force acting in the downward direction due to weight of the plate and upward thrust. So weight of the plate minus upward thrust. So 40 minus 25.43, that is equal to 14.57 Newton. Therefore, total force required to lift the plate up equal to total shear force plus 14.57. So that is equal to total shear force is F1 plus F2, that is equal to 86.4 plus 14.57. So that is equal to 100.97 Newton. So after finding shear force, you have to make extra calculation here compared to previous problems. So because weight is given, so upper thrust equal to weight of the fluid displaced, because when you are going to keep the body in some fluid, it is going to displace some quantity of the fluid out. So weight of the fluid displaced equal to, there's a formula you have to remember, weight density of the fluid into volume of fluid displaced. So weight density of the fluid rho is given, so rho into g into volume of the fluid displaced equal to volume of the plate. So you are going to get 24.43. Now weight of the plate minus upward thrust. Upward thrust means there is a buoyant force. Buoyant force you got it as 24.43. Sorry, this is 24.43. So 40 minus 24.43, you are going to get 14.57 Newton. Therefore, total force required to lift the plate up, that is equal to total shear force plus 14.57. So that is equal to 86.4 plus 14.57, that is equal to 100.97 Newton. So you have to just add the net force and shear force together, so that you should get total force. That's the modification. Total force is a summation of total shear force plus, that is the net force acting in downward direction, because weight of the plate is more than the upward thrust, so resultant is going to act in downward direction. So there's a concept here. Next problem, determine the bulk modulus of elasticity of a liquid if the pressure of the liquid is increased from 70 Newton per centimeter square to 130 Newton per centimeter square. The volume of the liquid decreases by 0.15%. So this problem is related to bulk modulus. So determine the bulk modulus, this is capital letter K. If the pressure of the fluid is increased from 70 Newton per centimeter square, there's an initial pressure is given. So to 130 Newton per centimeter square, there's a final pressure. The volume of the liquid decreases by 0.15%. So it is given percentage. So there is a volumetric strain. V divided dV divided by V, that is equal to 0.15. So initial pressure equal to 70 Newton per centimeter square, final pressure equal to 130 Newton per centimeter square, dP equal to increase in pressure, that is final pressure minus initial pressure, 130 minus 70, that is equal to 60 Newton per centimeter square. So decrease in volume, that is equal to 0.15 percentage. So decrease, that is a negative. So minus dV divided by V equal to 0.15 divided by 100. Why divide by 100? It is percentage. So 0.15 divided by 100. Therefore bulk modulus K equal to increase in pressure divided by volumetric strain. So that is equal to dP divided by minus dV divided by V. So that is equal to dP value we got it as 60. 60 divided by 0.15 divided by 100. That is equal to 4 into 10 to the power Newton per centimeter square. You need not convert here to pressure value. Otherwise you can convert Newton per centimeter square to Newton per meter square just multiplying by 10 to the power 4. So you are going to get the value of bulk modulus as 4 into 10 to the power 4 into 10 to the power 4 Newton per meter square, or 4 into 10 to the power 8 Newton per meter square. This is the value of bulk modulus. Last problem, what is the bulk modulus of elasticity of a liquid which is compressed in a cylinder from volume of 0.0125 meter cube at 80 Newton per centimeter square, pressure to volume of 0.0124 meter cube at 150 Newton per centimeter square pressure. So this is again problem related to bulk modulus. So initial pressure is 80 Newton per centimeter square, corresponding volume is initial volume, that is 0.0125 meter cube. Final pressure is 150 Newton per centimeter square, corresponding volume is 0.0124 meter cube. So solution, initial pressure equal to 80 Newton per centimeter square, final pressure equal to 150 Newton per centimeter square. So dP equal to increase in pressure, that is final pressure minus initial pressure. So 150 minus 80, that is equal to 70 Newton per centimeter square. Therefore initial volume equal to 0.0125 meter cube, it is given in question. Final volume equal to 0.0124 meter cube. So decrease in volume, you can see the value, volume is going to decrease, pressure is going to increase. So pressure is inversely proportional to volume. So decrease in volume equal to 0.0125 minus 0.0124. The initial pressure minus final pressure, or you can initial volume minus final volume, because you are going to consider higher value into consideration, because there is a decrease. Decrease means it is minus only, so you can consider minus also. It is left to you, 0.0124 minus 0.0125. So that is equal to 0.0001 meter cube. Therefore bulk modulus K equal to increase in pressure divided by volumetric strain. So increase in pressure, that is dP, divided by volumetric strain, that is minus dV divided by V. So increase in pressure we got it as 70. 70 divided by change in volume or decrease in volume is 0.001 and initial volume, that is V, that is 0.0125. So 70 divided by 0.0001 divided by 0.0125. So that is equal to 8.75 into 10 to the power 4 10 to the power 3 Newton per centimeter square. Here also no need of converting to Newton per meter square. If it is confusing, so means you can convert to Newton per meter square. So just by multiplying 10 to the power 4. So 8.75 into 10 to the power 3 into 10 to the power 4 Newton per meter square. Or that is equal to 8.75 into 10 to the power 7 Newton per meter square. This is the value of bulk modulus. So these are the problems related to bulk modulus and with respect to shear stress. Okay, thank you.